Hello everyone, welcome to AVLSI session number 4. So today we are going to see the revision of MOSFET small signal model, and then we will derive the expression of GMB. So let's start with fundamentals of amplifier requirement. So in a voltage amplifier, input will be a voltage and output will be an amplified form of that input voltage. So the requirements of an amplifier will be gain of the amplifier should be very large, input impedance of an amplifier should be very high, and output impedance should be very low so that it can drive any load. And last point will be linearity. This is very important. Amplifier should be linear. That means output should be linear with respect to input. Okay, so all these four requirements of amplifier should be satisfied. Now let's talk about some facts about the amplifier, about the MOSFET. So MOSFET as a device amplifies small time varying signals. Now why small time varying signals? This is required for the MOSFET to be linear. So very shortly we will signify why small time varying signals. Then MOSFET acts as a voltage dependent current source. So you see the expression of MOSFET, ID is given by Kn times VGS minus VTO the whole square. So this Kn and VTO are normally constants, right? So ID is directly proportional to VGS square basically. So that means your MOSFET converts a voltage to a current, a voltage which is input voltage VGS to output current ID. Fine. So hence it is a voltage dependent current source. Next, what we will do is we will superimpose a DC with a small signal AC. Okay, with a goal to make an MOSFET amplifier. So here is my circuit. I have the MOSFET over here, N channel MOSFET. We have connected the resistor RD and tied to the ground, connected to the VDD. And at the gate side, we have connected a microphone, short form for mic. And we have also superimposed a DC value, a biasing value of VGG. Now, why this biasing value is required? This biasing value is required so that my MOSFET should be, VGS value should be greater than VTH value. Okay. So this mic or microphone will act as a small time varying AC quantity. Okay. This is the representation of your mic signal, which is given by Vm sin omega t with a positive peak at Vm and a negative peak at minus Vm. Okay, that's about the input curve. Now what we will do is we will superimpose your transfer curve with this small signal time varying signal. Okay, so what really happens is I will be highlighting it very soon. So what we will consider is we will consider for the transfer curve, that is VGS versus ID curve, it's an exponential curve, right? So we'll consider a small segment of this exponential which is acting approximated as a straight line. Okay, so this will act as a slope, or we can call it as a straight line. So within this small range, you superimpose your time varying AC signal. Okay, so and the middle of this point will be my Q point. So Q point will be IDQ, which is a DC value, and VGSQ, which is again a DC quantity. Okay, so around this DC quantity, your AC quantities will revolve. So let us see what is my input. So input is a combination of a AC as well as DC. So it has a VGG biasing, which is a DC quantity, and there are small variations in VGS, which is Vm sin omega t. So here how the inputs looks like. Okay, a time varying quantity superimposed with the DC quantity. Fine. These are represented in the orange color waveforms over here. As you can see, it is well within this limit where your transfer characteristics is almost a straight line, right? And if this is within the limit, then your output variations, that is the variations in the current ID, are also within this range. Okay, and those variations can be just wait a second. Okay, so these are the small variations in ID which are revolving around the biasing point IDQ. So this is the picture over here. We have small variations in ID, which is delta ID. This is my AC quantity, and this IDQ is, this is my DC. Okay, so that's how we get a current at the output if you apply a small variations in VGS. So the important point over here is we are linearizing the non-linear transfer curve of a MOSFET. So that means in short, we are linearizing the non-linear characteristics of MOSFET, okay, by operating within a small range. So that's why we say small time varying quantity which is within this linear range. So if you, what will happen if you go beyond this linear range, there will be distortion in the output. So that is what is happening exactly, right? So that's how we MOSFET act as a amplifier. Now, why small signal? Well, we have seen already. Let's just read it out. So idea for a small signal is to consider a small segment of an exponential curve to be linear. Okay. So for that, your AC input should be small signal to be within this linear segment. That is what we are talking about over here. Okay. Your AC signal should be within this linear segment of this transfer as well as the combined time response. Okay. Now let's proceed ahead. So let's start building up the small signal model. So we already know the GM. GM is the MOSFET transconductance. So GM is basically the slope of the transfer curve, as you can see over here. It's given by delta ID upon delta VGS. So this slope is a constant, right? So hence the GM value also will be a constant, and but it will be a it will be a ratio of the change in the quantities, that is change in ID upon change in the VGS at VDS constant. Its unit is milliampere per volt. Okay, so if we rewrite the same expression as follows, we can write delta ID, which is changes in ID, is equal to GM times, which is a constant, into delta VGS, which is the small changes or variations in the VGS value. Fine. So this equations will whisper us that your gate to source voltage controls the drain to source current. Okay, that's a very, very important relation. This is the relation which we use in the small signal model. Fine. So we have a first version of a small signal model. Okay. So what is a small signal model? Basically, MOSFET is a non-linear device. So drawing a small signal model of a MOSFET will be like linearizing the non-linear MOSFET. Okay. So we are linearizing the behavior of a non-linear MOSFET in terms of small signal by drawing the small signal model. Fine. So here we are considering the three terminals, gate, drain, and source. The current flows between the drain and source. Between the gate and source, with the open circuit, because you have current is zero because of the very high input impedance. Why gate current is zero? Because of the presence of oxide layer in a MOSFET. What is present between the drain and source? Between drain and source, we have a voltage dependent current source. Remember, this small signal model will represent only the time varying quantities. So we have GM, which is a constant, into VGS, which are the variations in the gate to source voltage. And what did we learn from the last equation? Variations in the drain current is given by GM times the variation in the gate to source voltage. So over here, this GM into VGS is actually representing changes in ID. Okay, small variations in ID represented by delta ID. Fine. So that is what we have for the first version of the MOSFET. Yeah. Next, we have small signal output resistance RO. We have seen this before. So RO is the output resistance of the MOSFET in the saturation region. So it is given by the formula. RO is 1 upon slope, where slope will be delta ID upon delta VDS, which is again a constant slope. So RO value will be delta VDS upon delta ID at a constant value of VGS. So RO represents the small signal output resistance of the MOSFET biased in the saturation region. Okay, it is approximately given by the formula 1 upon lambda IDQ. Fine. So yeah, so this is about the small signal output resistance and RO. So what we will do next is we have to accommodate this behavior of RO in this model, because earlier in the first version of the model, it was an ideal MOSFET. So lambda was equal to 0. So now if lambda is non-zero, we have to consider its significance, right? So its effect will be considered. So that effect is captured by having a resistance, a linear resistance of value RO connected between drain and source terminal. So what does RO will represent? The RO will represent a slight increase in the current due to increase in the VDS value. Okay, so that means it will represent the changes in VDS divided by the changes in the ID value. So that's a second version of a small signal model of a MOSFET with channel and modulation parameter. So this small signal model is derived under the assumption that VSB is equal to 0. That means the source terminal and the body terminal are at the same potential. That is the assumption. Okay. Now, these are some stuff which you can relate. Fine. Okay. So let's move on to our main topic today, which is small signal model of a MOSFET with body effect. Now, in the last session, we have seen the effect of body effect, that it affects the MOSFET parameters like VTH, RON, RO, GM, and ID, right? So we have to accommodate its effect in the small signal model. So let's draw a 4-terminal analog MOSFET symbol. So as you can see over here, it has 4-terminal: gate, drain, body, and the source. Between the gate and source, we have VGS. Between the drain and source, we have VDS. And between the bulk or the substrate and the source, we have VBS. Okay. So this is our normal model, which we have seen earlier, right? GM, VGS, current source, RO, in parallel, we have RO, right? So the current flows into the drain terminal and leave the source terminal, right? So yeah, and here the voltage is across VDS, and here it is VGS. Fine. So this is the model we have already seen before. Now, in order to accommodate this VBS value, we have to draw it like this. Fine. Normally, what happens in an integrated MOSFET, that means if we are manufacturing the MOSFET on a chip, on a silicon chip, the bulk terminal of the NMOS is connected to the ground. Bulk or the substrate terminal, we can say. So bulk is normally connected to the ground. Source voltage may not be connected to the ground. So there will be a potential difference between the body, between the bulk terminal and the source terminal, which is represented by a voltage over here, VBS. Okay. So rest all the entire model remains the same. The voltage across the the RO over here is VDS. Okay. Drain voltage is measured with respect to the source. Gate voltage is measured with respect to the source. And here we have the current which is entering the drain terminal. Correct. So this current should be equal to this current ID, right? Because the current entering and the current leaving here at this point, source point, should be same. Correct. There should be same current flowing into the MOSFET, in spite of body and the bulk and the source terminal being at different potential. The current should flow in this direction as it is shown over here. Correct. And yeah, let us move ahead. So current is in this direction. So what we will do is we have to accommodate this behavior. Accommodate this VBS value into the small signal model. So how do we do it is, there is a current flowing between the, let me go over here. Yeah. So current is in this direction, ID, and current is from left to right in this direction. It is entering the drain terminal. Correct. So that information over here with the body effect, that is VSB is not equal to 0, is captured by a current source, which is given by the formula GMB into VBS. Now, why GMB into VBS? Because if you look carefully, the current which is flowing over here, this should be the same current which is leaving the drain current. The drain terminal. Correct. And if you see carefully, what is the relation between your VGS and VBS? Can anyone tell me what is the relation between your VBS and VGS? VGS, if you see carefully, is same as your VBS value. VGS is same as VBS value. They are equal in magnitude. Okay. So VGS is equal to VBS. That means this current source, we can tie it between the drain and the source terminal. Okay. And the current direction also will be same. So GM VGS. Okay. This is also the small, fluctuate variations in the drain current. GMB into VBS. This is also representing the small changes in the drain current due to the non-zero value of VBS. Okay. If VBS was 0, there would have been no current source connected over here. But since there is a difference between the body and the substrate terminal, the body and the source terminal, your GMB into VBS is coming into picture. Agree? Fine with this concept? You have understood why the current direction of this current source is same. This is also a voltage dependent current source, right? That is representing GMB is representing the transconductance of the MOSFET due to VBS. So indirectly we can say that the bulk terminal is acting as a second gate, because it is also controlling the current flow between the drain and the source terminal. Earlier, we have the gate, which is the controlling terminal. Voltage across the gate and source is controlling the current, the changes in the current as GM into VGS. Now, because of the bulk value not being connected to the same as your source voltage, we have their current ID is also being controlled by VBS value. Okay, so this is my small signal model of the MOSFET with body effect. Okay, so you can have a take a look at it carefully. We will be drawing the small signal model with the body effect of MOSFET many a times for many derivations. So this is a very, very important concept. If it is not clear, please get back to me. I will repeat it again if you want. Okay, fine. So let's proceed forward over here. So this is the same circuit, just some theory about it. Correct. So due to body effect, the bulk potential influences VTH, correct, and hence VGS minus VTH value will change. Fine, I have already talked about that the bulk terminal is acting as a second gate terminal, and over here the drain current, because it is a function of bulk voltage given by GMB into VBS. Okay, this is GMB into VBS. Let me change that. Okay, wait a second. Yeah, so let me change this quantity. Okay, so since the bulk terminal behaves as a second gate, since the drain current is a function of the bulk voltage given by GMB into VBS. So that's what we have said, the bulk terminal will act as a second gate because the drain current is flowing from drain to source, represented by the fluctuations in the drain current is represented by GMB into VBS. Okay, so modeling this dependence, modeling this will be by a current source connected between the drain and source between given by the value GMB into VBS. So that's just a theory which we are talking about. Now let's move ahead. This GMB into VBS, let me just copy it again from here. Wait a second. Okay, let me try to copy this expression again. Okay, yeah, so now it is proper. So GMB into VBS will represent the effect of VBS for the current ID. Okay, so the value of this current source GM into VBS is given by the formula. The value of this current source is GM into VBS, where GMB is given by the formal definition as delta ID upon delta VBS. Anyone remembers what was the definition of GM, transconductance of the MOSFET? It was given by delta ID upon delta VGS. And there is no surprise that the GMB, which is the transconductance of the MOSFET with body effect due to VSB, is given by the formula delta ID upon delta VBS, given by the equation number 1.1. So kindly note down this definition. This is very, very important. GMB is given by delta ID divided by delta VBS. Okay, so now let's go back to the small signal model. Here, the drain current is represented by drain current variations are represented by three quantities: GM into VGS plus VDS upon RO plus GMB into VBS. So this drain current will be given by these three addition of these three variations. Okay, so remember the drain current is already small single quantity. Fine. So your drain current is a function of, it's an addition of three terms: GM VGS, VDS upon RO, and GMB into VBS. Okay, so just remember it. I will keep this window open for some time. If you have a doubt, you can ask. So let's proceed for the derivation for GMB, expression for GMB. Okay, let us start. Expression for GMB. For your information, this is a very important derivation, which its result will be used in many other circuits and concepts. So let us start. GMB is the transconductance of the MOSFET due to VSB value being non-zero. In the saturation region, GMBs can be expressed as GMB is equal to delta ID upon delta VBS, where ID expression is given by half mu n Cox W over L VGS minus VTH the whole square. So we have to partially differentiate this expression of ID with respect to VBS. Now, if we partially differentiate this expression, we have over here half of mu n Cox W over L. This VGS minus VTH the whole square. You know, this VBS value is dependent upon VTH. How? Let us see. So this is the expression of VTH. So if you partially differentiate this with respect to VBS, there is a term VSB over here. That means VTH is not a constant. Fine. So what we will get if I partially differentiate this, we get half mu n Cox W over L is a constant. We'll get twice VGS minus VTH into minus of, because we have minus VTH, minus of delta VTH upon delta VSB. Actually, it should be here also it should be delta VSB. Just let me make the correction. Okay, so I've corrected that. So here we get over here half mu n Cox W over L twice VGS minus VTH into minus of delta VTH upon delta VBS. Okay, so that's how we get, because your partial derivative with respect to VTH is not a constant over here. VTH is a function of your body to source voltage. So hence we are getting over here another partial derivative minus of delta VTH upon delta VBS. See, this point is very important. Now 2 and 2 will get cancelled, and we can write GMB is equal to mu n Cox W by L VGS minus VTH into minus of delta VTH upon delta VBS. Okay. Now in the saturation region, the GM value is given by mu n Cox W over L VGS minus VTH. Here it is the formula. So we can replace this term by GM. Okay. So we can write GMB is equal to GM into minus of delta VTH upon delta VBS. This is a very important relation again. This we call it as equation number 1.3. Now our new aim is to find the value of delta VTH upon delta VBS. Okay. The VTH formula is given by VTH is equal to VTHO plus gamma into bracket open square root of mod of twice phi f plus VSB. Okay, minus square root of mod of twice phi f, the entire bracket closes. Okay, now instead of finding delta VTH upon delta VBS, we will find delta VTH upon delta VSB. So we can write delta VTH upon delta VBS is equal to minus of delta VTH upon delta VSB. Fine. So let's continue with this. So we are finding the partial derivative of delta VTH with respect to delta VSB. So we have the expression of VTH over here, which is given over here. Now let's see term by term what is the value. Okay, is it clearly visible? Yeah, fine, thank you. So delta of VTH upon delta VSB will be the first term. VTHO is a constant, so the differentiation of a constant value will be 0. Next we have gamma. Gamma will come as it is. Then we have over here a mod of twice phi f plus VSB the raised to half. So what is the differentiation of that? Half into mod of twice phi f plus VSB raised to minus half. That means that this square root of mod of twice phi f plus VSB will come in the denominator. Correct? So that's the differentiation for this term. And twice phi f basically value is a constant. Twice phi f is a constant. value. So its differentiation will be 0. So here we have written 0. So this is what we get. Delta VTH upon delta VSB will be gamma divided by twice square root of mod of twice phi f plus VSB. Okay. So here we want to write the expression of delta VTH upon delta VBS. So it will be minus of gamma divided by twice into square root of a mod of twice phi f plus VSB. That's a very important equation 1.4. That is also very, very important to note it down. Now, from this expression of 1.4, actually this should be 1.3. Okay, instead of 4, it should be 1.3. Let me just change this, because 1.3 equation is this. Correct? What does the 1.3 equation tells us? GMB is equal to GM times into minus of VTH upon VBS. And we have found out the value of VTH, delta VTH upon delta VBS. So we'll substitute it over here. Okay, let me add over here, 1.3. So from equation 1.3, we can write GMB is equal to GM times. Now this is minus, and we have to find minus of delta VTH upon delta VBS. So this will become plus. Okay, I should repeat again. In the expression of 1.3, let us wait, it is loading actually. Yeah, in the expression of 1.3, GMB is given by GM times minus of VTH upon minus of delta VTH upon delta VBS. So this minus sign is over here also, correct? So hence it will become plus. So this is a very, very important relation. GMB is given by GM into gamma divided by twice square root of mod of twice phi f plus VSB. So please take a print screen of this equation 1.5, or you write it down in your books. Okay, very, very important. Remember it, by heart it, whatever you do, don't forget it. Okay, so this expression gamma divided by twice into square root of this term can be represented by eta. So GMB can be written as eta times GM. This is also very, very important relation. So eta will be GMB upon GM. Okay, so it is equation number 1.5, 1.6, and this eta value is extremely important. Okay, so now there are some observations from this derivation of GMB. So if you look carefully from this equation number 1.5, your GMB is proportional to gamma value. It will also suggest that your GM into VGS and GM into VBS have the same polarity. Okay, and yeah, so these are the observations which we have seen. So we have derived the expression of GMB. Okay, so GMB expression will be given by equation number 1.5, which is GM times gamma divided by 2 into square root of mod of twice phi f plus VSB. So that's the derivation of GMB. If you have any query, you can ask now. I'll keep this screen open for some time. Sorry, I'll keep it aside. So that's how we started. I'll slowly proceed ahead so that you can go through all the steps again. And here we are finding out delta VTH upon delta VSB. Here we partially differentiate the VTH expression, and finally we get delta VTH upon delta VBS, and we finally put it back in this equation, and we'll get this term GMB expression. Okay, now one more thing, this model which we have seen over here is valid for low frequency and mid frequency. If we also want to consider the effect of high frequency, we have to go for the complete small signal model, which is shown in the last topic over here. Okay, so this represents the complete MOSFET model. The complete MOSFET model is shown over here. Okay, so it contains all the inter-electrode capacitance. It is valid for low frequency, mid frequency, also high frequency. As you can see, it is already accommodated GMB into VBS term. So that small signal model remains the same. In addition to it, we have all the extra capacitors which you see, interelectrode capacitors, which become active at very high frequency. So we have between gate and body VGB, between the source and the body we have VSB, between the drain and the body we have CSB and CDB. CGB, CSB, and CDB. Also between the gate and the source we have CGS, and between the gate and the drain we have CGD. So we don't have the analysis of it. That is analyzed in whenever we consider the high frequency analysis of any MOSFET circuit. That time we use this all the information. Okay, so this is just quite a bit of information given to you. When we include the interelectrode capacitances in the MOSFET model, it works for all the frequency ranges. Okay, so now let us move on to the next topic for today. Okay, let me go to full screen mode. Okay, so just give me 5 minutes. I'll complete the two numericals or intuitive questions which are present over here. Fine. So let us consider question number 1. So for the following circuit, we need to plot the on-state resistance, of M1 as a function of VGS. Okay, so over here the drain terminal is left open, the gate voltage is VG, and the source voltage is connected to 1 volt. Fine. So Vs is equal to 1 volt over here. Ron is given by the formula 1 upon delta ID upon delta VDS. That means Ron is actually given by 1 upon GM. And GM is a function of VGS, correct? So GM is given by delta ID upon delta VGS. Ron is, we have seen that we have derived this expression. Ron is given by 1 upon mu m Cox W by L VGS minus VTH. That means there is a direct relation between my Ron and my VGS. And how they are related? They are inversely related. That means Ron, whenever VGS increases, Ron value will decrease. And whenever VGS decreases, Ron value will increase. From this circuit, what is VGS? VGS is nothing but VG minus VS, which is VS is 1 volt, so VG minus 1 volt. Now, the drain terminal is kept open over here. So we presume that there is no current flow. Now, if the device M1 is on, it will operate in the deep triode region given by this formula. Okay, that is the formula. If the device is on here, over here, it will operate in the deep triode region. Then only we will consider the Ron value, right? Now, let's consider this. If VGS value is less than VTH, what is VGS now? VG minus 1, correct? So that means if VG value is less than 1 plus VTH, my M1 transistor is off and my Ron will be infinity. Whenever my transistor is off, my Ron value will be very, very high, which is infinity. Now, we know that for a MOSFET to turn on and enter into deep triode region, your VGS value should be greater than VTH, correct? So here, actually here it should be VG value. So VG value has to be greater than, because here it is VG value less than 1 plus VTH. Here it should be VG value greater than 1 plus VTH. Okay, for this value of VG, MOSFET has turned on into deep triode region, and we have this relation of Ron. This relation is between Ron and VGS. They are inversely related, correct? So if VGS will increase further, your Ron will drop to 0. Fine, let us see that how it is there. So this is the plot of Ron versus VGS in general. So what is this point? This point is actually VGS minus VTH, right? What is VGS? VG minus 1 according to the numerical. So over here, if let's consider some numbers. Let's consider mu1 Cox is 50 microampere per volt square, W by L is 10 volt, and VTH is 0.3. So Ron value will be given by 1 divided by 50 microamperes into 10 into VG minus 1 minus 0.3. So what can we say is that if VG value becomes close to 1.3, if VG value becomes close to 1.3, what will happen to Ron? Ron will become infinity, correct? And if VGS value goes on increasing, what will happen? your R on value will drop to 0, will be decreasing drastically. So this is the point. Okay, this is the point over here. VGS minus VTH it is actually fine. So whenever VG reaches 1.3, R on will be infinity, and as the value of VGS increases, your R on drops down. Same can be considered over here. Okay, this is nothing but VGS minus VT. So if VGS is less than VT value, I mean this quantity VG is less than this value, the gate voltage is less than 1 plus VTH, then what will happen? The MOSFET is off. Correct. At this point of time, whenever VG becomes equal to 1.3, here in this case, whenever VG becomes equal to 1.3, R on goes to infinity. So with the help of these two curves, we can explain the behavior. I mean, with the help of these numbers, we can explain the behavior of R on versus VGS. Okay, so I'll keep it there keep it open for your reference so that we can have a look. Okay, let's move on to the last numerical for the day, numerical number 2. So for the following topology, plot the transconductance as a function of VDS. So we have to plot DM versus VDS. So let's consider this MOSFET over here. So we have applied the drain to source voltage. The current is flowing from drain to source ID, and this MOSFET name is M1. Its gate terminal is applied a bias value of VB, which will keep this MOSFET maybe in the saturation or maybe in the triode region. Let's see that. Okay. So over here, let us start. VGS value is given by VG minus VS. VG value is VB actually, and VS is connected to the source terminal is connected to the ground. So VS terminal will be 0. So VGS will be equal to VB. Correct? As long as VDS is greater than or equal to VGS minus VTH, your M1 is in saturation. And whenever M1 is in saturation, the drain current is relatively constant. Now, we know the formula for GM in saturation. It is given by square root of twice mu and Cox W by L into ID. Now, if ID is constant and mu and Cox W by L is, they are technological constant, your GM will also be constant. That is the learning over here. So that means if the MOSFET is in saturation, the drain current is a constant, and from the expression of GM also remains constant. Okay. Now let's consider the other case. When VDS is less than VGS minus VTH, that means my M1 is in triode region. We have derived the expression of GM for the M1 for the transistor in the triode region also. So GM expression was given by mu and Cox W over L into VDS. Okay. So in the triode region, when the value of VDS decreases, your drain current also decreases. Hence, your GM also decreases. So we can say that your GM value will drop if your device enters into triode region. This is very, very important. Okay, your GM value will drop if the device enters into triode region. So let us see if this is the plot. Yes, it is. So what we have discussed so far, whenever VDS is greater than VGS minus VTH, my MOSFET is in saturation. And whenever my MOSFET is in saturation, my drain current is constant, hence my GM value is constant. As soon as I enter into my triode region is whenever VDS is less than VGS minus VTH, my device enters into triode region, and in the triode region, my GM is directly proportional to VDS. So if my VDS value is decreasing, my GM will also decrease, and if my VDS value is 0, my GM also will be becoming 0. Okay, so that's a very important graph over here, GM versus VDS. That is what was expected from this numerical. So that's a very important learning. So in your analog VLSI circuits, for amplification purposes, we usually employ MOSFETs in saturation, because when we employ MOSFETs in saturation, its GM value will be higher than the MOSFET in the triode region. In fact, in this entire many circuits, mostly your MOSFET, mostly for some cases, it might work other than the saturation, but mostly MOSFETs operate in the saturation region. Okay, and we have seen this classic example over here. Okay, so that is all for this session, and I will also show it to you AVLSI 4.3 handout over here. This is the formula sheet, which is version number 2. Last time we have discussed up till here. So we have, one more equation has been added. Branch conductance formula of the MOSFET due to VSB. So this expression is added now. Okay. So you should also note it down in your book somewhere and maintain this entire formula sheet together. Okay. So with this, we have come to the end of this session. That's all what we have to cover today. And yeah, so we will meet next time with a new topic. So until then, have a good day and thank you.